Right here, let's consider a little bit about the DFT. We know that the DFT is defined, originally it's defined like this way. It was 1 over n. So this is the inverse DFT, and this one is the DFT. But the issue for here that when we converting this one, in fact this one corresponding to matrix product, so we can think about there is some transformation matrix will be exist to making the transfer matrix for normalize. I would like to use this expression. I just change the scaling factor for transform and inverse transform. The benefits for this definition, you know that in original definition, this was 1, and the inverse was 1 over n. But separating these two things, we can make it symmetric. You know that this part, consider this part, and also consider this one. Okay, it's a complex conjugate pair. Okay, so converting is just a product of the same the kernel. Okay, so we can make it symmetric by separating this scaling factor. So scaling factor is not that big issue in converting. So let's try to using these definitions. Then we can define the transfer matrix can be given like this one. Its component is 1 over square root n is this part, and the exponential j 2 pi over n times kn. So this one is a kth harmonic and nth element. So this is k is a harmonic index. Harmonic index is k, but the sequence index is n. So to find out kth harmonic, we need to sum up with respect to the sequence. So that operation can be interpreted in this way. T is DFT transform matrix. If we taking product transform matrix to the original sequence X, that's this calculations. Then we can get the spectral domain. But if you taking the transpose and the conjugate, that is expressed by Dega. Dega is a transpose and complex conjugate pair. Okay, then we can express the Dega is this one. So exponential 2 pi over n and nk. Okay, this j is changed to minus j because of this conjugate and the transpose. Transpose is changing the row and column index like that. So originally T was row index is spectrum index, the column is a sequence index. But in case of Dega, the row index becomes the sequence and the column index is spectrum. Okay, if we taking product between the inverse transform and transform, you know that this one is just the inverse Fourier transform. Okay, you can easily understand that by taking the Fourier transform and multiply the Dega as a multiplied the spectral domain, that becomes the same things. That's why it should be satisfy the identity matrix. If you consider this matrix product, is a mth row and nth column can be found by these productions. So nth row and mth column can be obtained in this product. These matrix product are expressed by the series summations. Then you know that this product can be expressed in these equations. You can replace the kn. Km is just the k and m, and kn conjugate is a plus j n over 2 pi and m product k. So if you replace the definition of the t and k on here and tkm on here, then you can find out that this result. Because of the basis function of 0 to the n minus 1, because of the orthogonality of the complex exponential function, if n is not equal to m, it should be 0. If n equals to m, it is 1. So you can find out that this one is just identity matrix. So diagonal term is 1, all the other off diagonal value is 0. So if you're using the symmetric DFT concept, the basis function is very simple. And by taking the transpose and conjugate, that is the inverse transform matrix will be obtained. There is 4 types of DCT, but at this moment I focus on DCT type 2. We have n sequence, and so xm will changing from index 0 to the n-1. So this is original sequence. But when we using the DCT, we take the offset is 1.5 minus 1.5, and minus 1 to the minus n is another mirror image is copied to the left side to guarantee the continuity at the boundary condition. So it is a even symmetry with respective to minus 1.5 point. So the even xm prime has even symmetry with respective to minus 1.5, and it has a period is 2n. So this is periodicity becomes 2n, and also xm is copied in the mirror image on here, and also it is repeated in the 2n period. If we shifting 1.5, then we shifting at this point as 0, then we can write the indexes. This is 1.5, this becomes the minus 1.5, then it's an even symmetry with respective to the 0. So in DCT2, we taking the offset is this point, so we need to add up 1.5 of the index. So in type 2, always this terms comes out. So different type has different offset value, but in this moment we are taking the symmetric offset. That's the 1.5. So when we take the DCT via basis function, this 1.5 is added here because of the symmetry. Okay, and inverse DCT will be expressed in this way. We take the summation only the half of them. You know that when we take the DCT, we summing over here only. And when you take the inverse of the DCT, the older the spectrum is a symmetry with respective to the offset point. But the DC component has a single variable, so that's why it is the 1.5 of x0, and the other terms is doubled like that. And this is a offset of the basis function. By use of those concepts, we can develop the DCT matrix. This is definition for the DCT. The definition of the DCT for xm sequence. By taking the summation of this one, we can have the DCT output. Add here that the cosine terms evaluate the mth index and the kth harmonic component. So that is a k harmonic and mth sequence expressed at here. So that's this value. So this cosine value expressed by this element. So you can easily understand this one is a matrix product. So we need to find out this value. That's the defined like that. Then the C matrix is a K low numbers. K means harmonic index, and M column is a sequence index. So kth harmonic component can be found by these summations. So M should be changing from 0 to the n-1. Okay, so 0 to the n-1. Then we have this expression. This is DCT transform, and we would like to develop the orthogonal and normality property. That is this one, as we have done in DFT. Okay, we talk about in the DFT. This is orthogonal and normal. Okay, the product becomes the unity. To make it this one, we need to normalize the 1 over square root n, both the DFT and inverse DFT. Similar normalization factor should be found to satisfy these conditions. So if we taking square of this one, the product between two different basis vectors, it will give this result. If k is 0, then that is 1n. If it is not, it should be 1n over 2. That's the this value. And to normalize this one, if k is not 0, then we taking this normalization factor. That's this one. And if k equals 0 case, we taking this normalization factor. Then we can guarantee that this C transpose times C becomes I. At this moment, C, you know that this is cosine value, so this is a real number. But in case of DFT, it is complex number because of complex exponential terms. That's why we are taking the DEGA. DEGA is a transpose and complex conjugate. But at this moment, we need only the transpose. Then it should satisfy these conditions. And we can express the DCT and the inverse DCT in this way. We define the cosine transform matrix C and normalize it to satisfy transpose to this C transpose times C becomes identity matrix. So this part becomes DCT, and C transpose X is inverse DCT. It's quite similar to DFT. We talk about T times X is DFT, and the T DEGA times X becomes the inverse DFT. If we using the normalized version of the kernel, then it's the inverse DCT is a DFT, or inverse DCT is quite simple. And okay, here is some example. If the sequence size is 2, then it's 2 by 2 matrix. So we can find out the C0M, 0 harmonic means that this law. So 1 of square root 2, these two things is this one. And the first law can be found by using this one. M can taking 0 or 1. K is also 0 or 1. So this is the DCT matrix for n equal 2. What about n equal 4? N equal 4 cases, you can find out the C DCT matrix like this way. This one is normalized DCT, so you can using this matrix to find out the DCT, or by taking transpose, it will give the inverse DCT. Shows a two-dimensional DCT shown here. In case of image, data sequence is given as a two-dimensional. One is x-axis column and the y-axis as a row. By taking the DCT, the spectral domain also has the row frequency index and the column frequency index are given in this way. So two-dimensional DCT can be written similar to the one-dimensional DCT like this one. But the issue is this one, there is a double matrix operations. So one is for the K1 and the other one is a K2 index. At here, if you see here, that is there is a two cosine transforms exist here, but the N1 and K1 and N2 and K2 is the index of this one. Similar to DCT, we can define the kernel matrix like this way. So this is the kernel matrix. That's the one of the matrices, this one. Okay, and we take the orthogonal and normalized factor is added to the this T matrix, then T transpose T should be equals to identity matrix. And to express this double matrix operation, we can express the transpose, the two-dimensional spectrum can be obtained by these two transformations. And here that the row index, X is matrix, row index is K1 and column index is K2. So the product are given like this when N1 and N2 are changing, K1, N1, and data is also two-dimensional. So N1 is row index, N2 is column index. And transpose T have N2 and K2 dimension. If you look at these index, so N1 and N1 and N2, N2 will cancel out. So by this product, K1 and K2 value will come out. This one is double integral operation are shown here. And what about the inverse DCT? If you're just producting T transpose at left side of the X, then this becomes identity, and the right side we product the T, then this becomes the T. So this is the the inverse DCT operation. One of the application of the two-dimensional DCT is image compression. JPEG image compression using that DCT conversion. The original image is split into 8x8 segment. So segmentation will be done first and remove the offset DC. Because the DCT and numerical operation should be done by use of signed number, but the image originally is an unsigned number. So unsigned number should be converted into signed number by removing the offset. And we take the DCT, and this procedure 4 is a quantized step. We have some standard quantization table. By use of that, we can drop out some smaller harmonic spectral component, and then we can compress the serialized data by use of Huffman code, and we can rebuild the image by use of inverse DCT, and by adding the offset we can make a compressed image. If we using the 8x8 image segment, we have to use the transformation matrix of 8x8. That's this one. You can derive it from here to here. At this moment n is 8, okay, so 2 over 8 is 1 over 2 and pi over 8, like that. So we can build up this table by use of this definition. And how are we going to use that one? Firstly, original segment is 8x8 image segment is applied here, and this original image is unsigned number from 0 to 255. So we need to remove the DC offset, and remove the DC offset is this one, and then we apply the DCT, two-dimensional DCT, and this is the two-dimensional DCT. Most of the value is non-zero. By use of the quantization table, by use of this one, we can round off the values. Then this table converted into this way, but most of them are 0. So we do not store the 0 value. Only non-zero value will be stored. That is how we're gonna compress the image in the spectral domain. And to reconstruct the image, firstly, we need to compensate the quantization table. When we quantize, we use this table. We divided this one like this way and round off, then this becomes this way. So to recover, we need to multiply quantization table again. Then this one is a reconstruction version of this one. So DCT is approximated in this way. So most of 0 are dropped. And take the inverse DCT and adding offset, then we recover that the image. So that can be almost the same as original image. Here shows a Python example to demonstrate the JPEG image compression. OpenCV packages are used to display the image. I take the segmentation size is 8x8 image segmentation, as I explained in here. First, I read the image, and then build up the discrete cosine transform for the 8x8 matrix. That's this matrix is created on here. So this routine generate the T matrix to converting two-dimensional DCT, and I make the 8x8 blank image. The original image is stored here, and quantization table 50 will be created on here, and the quantization table 80 will use this one. I have two different quantization methods. One is a Q50, the other one is a Q80 table. And to store the DCT value for Q50 and 80 is a variable R defined it here. And this one is a standard Q80 table to quantize the JPEG image, and Q50 table is this one. Both of them is 8x8 matrix. And I would like to counting the non-zero component for each image. This one is the original one. This one is a Q50 table compression, and this one is Q80 table compression. So at here, I calculate the segmented image, each one. So firstly, each segment 8x8 image is converted here. Image 01 is the original image. Okay, this one. The original image is a 512 times 512. So this is a big image, but we segmented 8 by 8. So at one time, I would like to converting 8 by 8 image matrix like that. This one is the first segment, one of the segment, and converting into a signed number. And then I take the DCT by product of the T transpose. You know that this operation is just this operation. Okay, that is done matrix operation out here. The done means the dot product. NumPy package has a dot product provided here. So this is the dot product for images data. Image at this moment this is M. Offset removed value. Offset removed value is transpose T, and the T is product like this way. And then I just count the number of non-zero value. The original is reset, and I counting the number of non-zero value that we have to store. And the next, I round off by use of Q80 table. Okay, that's this table. By dividing this image, the number will be reduced, and the round off, it means that if the value is less than 0.5, we can make it, we remove the value, make it 0, and multiplied Q80. So many of the data is removed by use of this technique. When you consider image pixel to pixel, the change is not that big, so it means it's quite most of the image information stored in the low frequency component. But a higher frequency is usually the not that important. It is usually noise, so we can remove those parts by use of these techniques, by use of this Q80 table. And then I counting the number of non-zero component from here. And similarly, I take the Q50 table quantization. That's the quantization step, and then counting the non-zero value. And from here, I take the inverse DCT for Q80 and Q50 table, and regenerate image for compressed by Q50 and Q80. And that is reconverted into image value, and calculate the compression ratio and show the image. So let's learn this one. Then okay, I think I need to change the path from here and then learn again. Okay, then okay, you can see here that this is a Q50 and Q80, and this is the original data. The compression ratio, you can see here that Q50 has it's almost at 11%. 11%. This one is at 23%, like that. Let's compare that this is the original image, and this one is compressed. The amount of data is only 23% of the original data, so almost 80% we are removed. So we can compress this much. And what about this one? We remained only 11%. It means almost 90% is this removed, but still the image is quite normal. Okay, so this is one of the technique to compression. Okay, if you carefully look at the light on here, it's slightly different, but most of the images are conserved.